PhD from University of Science and Technology of China. He did his postdoc at California State University with Professor Donna Shen, and then at Princeton University with Professor Duncan Haldane. After that, he went to work at the Los Alamos National Lab, and then he joined Westlake University as a faculty, I think around 3 years ago. Right? I also would like to mention Westlake University is, I think, the second and probably currently the only privately funded all-around university in China. I was there more than 1 year ago. It was a very impressive place with a very ambitious long-term plan. Also, Professor Zhu Wei's research interests include strongly correlated electronic and magnetic systems, with a particular focus on the fractional quantum Hall effect. He is the expert on the numerical analysis of such systems, and I think he's particularly one of the leading experts on the application of the density matrix renormalization group in fractional quantum Hall systems. And this is highly non-trivial, given that we are dealing with a two-dimensional system with strong interactions. And today he's going to share with us his work on the interface between the non-abelian Pfaffian and anti-Pfaffian topological orders in fractional quantum Hall fluids. So without further ado, let us welcome Professor Zhu.
Yeah, thank you. Yeah, thanks for invitation from Yangbo. Yeah, so this is my great pleasure to have this chance to present our recent work here. I would like to discuss the interface between Pfaffian and anti-Pfaffian topological order, and I believe the physics presented here has implications for the nature of the 5-half quantum Hall effect in experiment. So this is outline of my talk. In the first part, I will briefly introduce the experiment, thermal Hall experiment on the fractional quantum Hall 5-half state. And this is also the motivation for this theoretical work. In the second part, I will introduce you the theoretical consideration and the related numerical test. And in the last part, I will show you how to connect our theory to understand the nature of the 5-half state and how to understand the thermal Hall experiment from our theory. Okay? So fractional quantum Hall effect at the Fitting factor 5-half. Fitting factor equals 5-half is a mystery in condensed matter physics. I think this is the first experiment identification for the fractional quantum Hall effect at the Fitting factor with the even denominator. And this Fitting factor is surely beyond the description from the Laughlin state, so its nature has attracted lots of the interest. However, after 30 years study, I believe currently, so far, we don't have the conclusion on the nature of the 5-half state. As I show you here, many people propose the different wave functions or different theories to understand the nature of 5-half state, ranging from the abelian state to non-abelian state. But currently, we don't have the exact answer to the nature of the 5-half state. In 2018, one group at Whitman Institute performed the first thermal Hall measurement on the 5-half state. And the message or information from this experiment has important implication to the maybe holds the key to the nature of the 5-half state. And also this is the main motivation for our current work. So here I would like to describe the main results from this experiment here and show you some discussions. And in the left picture, so this shows the electron Hall conductance measurement from this experiment. You will see that there is a dip, as shown the red line, in the longitudinal resistance, which shows this state, 5-half state, is an insulator state. And also, if you check the electric Hall conductance, which shows a plateau near the 5-half, as shown the blue line here, so which shows that the electric Hall conductance quantized to the 5-half in unit of the electric conductance unit E²/h. So this observation from the electric Hall conductance shows that this is at the Fitting factor 5-half, this is a fractional quantum Hall effect. And the reason is easily understand that there is a fractional charge at this Fitting factor. Okay, and the next question is that The next step experiment is the group perform a temperature field across this sample as shown in this cartoon picture, and they measure the energy current in the perpendicular direction. What they conclude is that the thermal Hall conductance is close to the value of 2.5 for the 5-half state, as shown here. If we take this message from the experiment group, that is, the thermal Hall conductance is close to the quantized value, that is 5/2 in unit of the thermal Hall conductance unit. So this information is important because this information tells us that the nature of the 5-half state is non-abelian. So the reason I would like to show you in the next slide. So we know for the parallel gapped topological order, there is a so-called bulk edge correspondence. That is, the physics of the gapless edge state is related to the topology in the gapped bulk. So in this case, so in many cases, we would like to analyze the effective theory of the edge mode directly instead of the bulk state. So for fractional quantum Hall state, usually we can divide it as edge mode into two classes. One is called the charge mode, and the other class is called the neutral mode. The charge mode carries the electric charge unit, and so it can carry the electric charge. But the neutral mode is charge neutral mode. So in this case, if we calculate the electric Hall conductance, only the charge mode contribute to the electric Hall conductance. Okay, but if we calculate or measure the thermal Hall conductance chi xy, as I show you here, both of the charge mode and the neutral mode will contribute. So if we can combine the thermal Hall conductance and the electric Hall conductance together, it is helpful to identify or pin down the nature of the quantum Hall effect uniquely. So here, in the last line, the thermal Hall conductance is related to the central charge carried by each edge mode, and the central charge is a unique number to identify the underlying theory of the gapless edge mode. So if we calculate for the one-dimensional gapless edge mode on the boundary of the two-dimensional gapped topological order, we know the energy current can be calculated exactly from the conformal field theory or from the Carroll-Lawton nuclear theory. So we know that based on the one-dimensional CFT, the energy current is proportional to the Carroll central charge C here. And in the definition of the CFT, C is the unique number to identify is the underlying nature of the CFT theory. Here I list the two simplest example here. For example, for the free Carroll boson mode, we know the Carroll central charge is 1. So we expect that the thermal Hall conductivity for the free Carroll boson is 1 in unit of the thermal Hall conductance unit. And another example is the free the Mariana fermion mode. In this case, the Carroll central charge takes 1/2, so we expect the thermal Hall conductance takes 1/2 also. And in this theory, so if we use this theory, we can conclude several important messages. For example, for all of the abelian quantum Hall states, since the edge mode constructed by the free Carroll boson mode, so the thermal Hall conductance should be some integer value for all of the abelian quantum Hall states. Only for the non-abelian states, the thermal Hall conductance can take the fractional value, since we can include, for example, the Mariana mode in the gapless edge mode. So here I would like to show you two examples here also. The simplest example is the abelian Laughlin state. For example, we consider the boundary separating the Laughlin 1/3 state from the vacuum state. We expect the free Carroll boson edge mode around the boundary. So in this case, if you count this single edge mode, you will see that the electric Hall conductance is quantized to 1/3 in unit of E squared over H, and the thermal Hall conductance is quantized to 1 in unit of the thermal Hall conductance unit. Okay, since this is due to that the single charge of free boson mode is 1, as I show you here. Another example is the non-abelian state. So think about the non-abelian Pfaffian state, and we see that here the edge mode become much complex compared to the abelian state. In this case, the edge mode is constructed from the free boson mode together with the one Mariana Fermi mode. In this case, you will get that the electric Hall conductance quantized to 5/2, and also the thermal Hall conductance quantized to 7/2. In this case, you see that the thermal Hall conductance takes the fractional value. So this is directly comes from the existence of the Mariana mode, which is the reason why this state is non-abelian nature. So a simple message is that if we have the fractional value for thermal Hall conductance measured in experiment, it is naturally to expect that the nature of the fractional quantum Hall state is non-abelian. So this is the reason that in the previous experiment that if we can conclude, if we can trust the experiment measurement from the experiment group, so this is a fractional value for thermal Hall conductance, so it leads to the non-abelian nature for this 5/2 state. Okay. So, the thermal Hall measurement or thermal Hall conductivity is complementary to the measurement of from the electric Hall conductance. This will help us to identify the nature of the fractional quantum Hall effect. So here I list a table that the predict the value for thermal Hall conductance and measure the value from experiment group. And from this comparison with theory, we can uniquely pin down the nature for different fractional quantum state. But here, for the states listed here, they are all abelian state. And the experiment I show you about is the first experiment in the non-abelian fractional quantum Hall candidate. Okay, and let's with this preparation, we can come back to the experiment, the thermal Hall experiment, as I show you above. Here, to explain or to understand the experiment observation, one of the leading candidates is so-called Pfaffian state. And this Pfaffian state was first proposed in 2016 in this paper. And if we write down the effective edge theory, we found that around the boundary, there are two counterpropagating modes. One is from the Mariana mode as a dashed line here, and the other one is a free boson mode as shown by the solid black now. Okay, so they are counterpropagating around the boundary, and if we count these edge modes together, we will get the electric Hall conductance equals to 5/2, and the thermal Hall conductance equals to 5/2 also. So in this case, we'll see that this this theoretical value is consistent with the experimental observation. So I believe this state is one of the leading candidates to explain the experimental observation. However, we have some problem here. The problem related to the particle Pfaffian state is that currently we don't know any physical model or physical Hamiltonian that is relevant to the experimental condition can realize this particle Pfaffian state as a ground state. Or that means if we start from some physical model or Hamiltonian that we believe to describe the experimental condition, if we diagonalize this Hamiltonian to obtain the ground state, we found that ground state is other state. The ground state is not this particle Pfaffian state. So this is one of the problems that we don't know how to realize this state in experiment, or what kind of the mechanism in experiment can realize this particle Pfaffian state as a ground state. Okay, so besides this particle Pfaffian proposal, we have other we notice that in theory we also have some other possibilities. For example, the Pfaffian anti-Pfaffian puddle state. If we check that check the table of the different non-abelian state or abelian state, we will see that the Pfaffian state takes the thermal Hall conductance 7½ as I show you above, and also its particle Hall conjugate state, we call it as anti-Pfaffian state. It takes the thermal Hall conductance 3½ So the nature simple consideration is that we can combine these two states together. That is, similarly consider a general cartoon picture that we consider in real space. In some of the region, we have the Pfaffian rich region, and in some of the region, we have the anti-Pfaffian rich region. If we combine this puddle-like state together, at the long length scale, we will recover a uniform liquid state with the average thermal Hall conductivity around 5½. So if you trust this, so this value is also close to the experimental observation. So people propose that in these 3 papers, people propose that this puddle state made of the Pfaffian and anti-Pfaffian state could be another theoretical candidate to understand the experimental observation. Okay, so the problem raised by this theoretical proposal is that can it be energetically favorable in the experimental condition or not? Or what kind of the mechanism can stabilize this theoretical proposal in the experimental condition? So this question is also the motivation for the current study. Okay, so here we just briefly summarize what we obtained from the experiment measurement. First, we introduced the thermal Hall measurement and thermal conductivity, and we see that the thermal Hall conductivity can detect both the neutral mode and the charge mode. So this is in contrast to the electric Hall conductance. Electric Hall conductance can only detect the charge mode. Okay, and also we found that the thermal Hall conductance is able to distinguish the abelian state from the non-abelian state. For abelian state, the thermal Hall conductance should be integer value, and for non-abelian state, the thermal Hall conductance could be the fractional value. So usually, the fractional value of the thermal Hall conductance is some kind of the strong evidence for non-abelian nature. So in this experiment, as I show you above, so the measure of the fraction, the obtained fractional value for thermal Hall conductance is their main conclusion for the non-abelian quantum Hall state for the 5½ state. On the theoretical side, the question is that if we take this fractional value for thermal Hall conductance, so how to understand it on the theoretical level? So one theoretical proposal is called the Pfaffian state, and the other theoretical proposal is called Pfaffian anti-Pfaffian puddle state. And today I will show you some of our theory to understand that how to stabilize the Pfaffian anti-Pfaffian state in the experimental under the experimental condition. Okay, so yeah, so to answer this question, to how to stabilize the Pfaffian anti-Pfaffian puddle state on the experimental condition, we propose to study the interface between Pfaffian state and anti-Pfaffian state first. So here we would like to ask a question before we go to the details, that what will happen or what will occur on the interface between Pfaffian and anti-Pfaffian topological order. So in general, so we have 2 expectations. The first expectation is that we expect some of the edge state or edge mode emerge around the interface. So this is easy to understand. Think about that we have a boundary separating the Gapless topological order from the vacuum. It is natural to expect the Gapless edge mode around the boundary, right? So here, when we put 2 topological distinct order together, we also expect we have the different edge mode around the interface. And in the weak coupling limit, that means you can think about the 2 states are separate far away from each other, and there is a vacuum separated these two boundaries, and you will see that the edge mode around the interface is just simply constructed by two groups of the edge mode from Pfaffian and from anti-Pfaffian state separately. And the next, you can consider introduce the tunneling effect across this interface. And when this tunneling become relevant, some of the edge mode, the counter-propagating edge mode will be gap out. And what's left in around the interface in the strong coupling limit is some of the neutral mode. And this neutral mode is Mariana neutral mode. And here, this procedure can be actually what I described above can be derived step by step by following the effective edge theory. That means you just write down the edge mode from the Pfaffian state and the edge mode from the anti-Pfaffian state, and then introduce the tunneling between this edge mode and gap out some of the edge mode propagate in the opposite direction, and you will get the final edge mode left on the interface. The answer is that you will have, if we assume there is additional O4 symmetry here around the interface, what's left on the interface is charge neutral Mariana mode. So here, the first step is that the first answer to the question is that we expect some of the edge mode around the interface. And here we elucidate that through the effective edge theory, in the strong coupling limit, only the charge neutral mode left on the interface and the charged mode are all gapped out. Okay, and the second effect, besides the chiral edge mode emerging around the interface, we also expect that there is electric dipole moment emergent around this interface. I would like to emphasize that this effect is usually overlooked, especially in the effective edge theory. So I would like to share with you some details to remind you this electric dipole moment effect. Okay, so let's think about the simple cartoon picture like here. So think about we have a boundary here, separating from a chiral gapped topological order from the vacuum. Okay, so this is boundary. And as I mentioned above, we naturally expect a chiral edge mode around the boundary. So here we elucidate the chiral edge mode as the red solid arrow here. This shows that the conducting direction is along the y direction. The velocity field is the Vy for the edge mode. Okay, and one important information is that we expect the Vy has the non-uniform distribution along the x direction. The reason is very natural. So think about in the bulk that is far away from the boundary. That we know in the bulk there is no chiral edge mode, so the velocity of the chiral edge mode Vy can be taken as a 0 in the bulk or far from the boundary. But we know that around the boundary, close to boundary, Vy is non-zero. So we expect that Vy along the x direction has a non-trivial distribution. Or we can think about the gradient of the Vy velocity field along the x direction is non-zero. So that is a partial Vy, partial x is non-zero for this simple setup. Okay, so if you take this message, we immediately see that for the quantum Hall state, which breaks the time reversal symmetry, and there is a viscosity force, which causes the F viscous applied on the edge mode, as shown by this blue arrow. So this viscous force is proportional to the gradient of the velocity field along the x direction, and also it is proportional to the eta h. Eta h is called the Hall viscosity. Okay, and please note that this viscous force is perpendicular to the direction of the velocity or the edge mode direction Vy. So this force is dispensionist and does not cost energy in this system. Okay, and if we only consider this viscosity force on the chiral edge mode, we will see that the chiral edge mode is unstable. So there should be some other force to counterbalance this viscosity force. So the counterbalance force comes from the electric force. That is around the boundary, or we know that the boundary will introduce the confining potential, and this confining potential will introduce another electric force, which is from the coupling between the electric dipole moment from the non-unitary, the non-uniform electric field from the confining potential. So the dpx is the emergent dipole moment around this around the boundary, or due to the chiral edge mode. And if we combine these two forces together to make the stable condition for the boundary, that means these two forces should be counterbalanced with each other and cancel. So we will obtain a condition for the dipole moment, which should satisfy this condition. The dipole moment per length, that is, the per length is the Ly is the length of the boundary. So it should be equal to the ratio of the Hall viscosity over the magnetic field B. Okay, and here in the next slide here, I would like to show you a very simple example to show you this dipole moment effect. So here, this example is again the boundary separating the Laughlin one-third state from the vacuum. So here we see that the dipole moment, according to the formula we derived above, it should be equal to the ratio of the Hall viscosity over external magnetic field B here. And Hall viscosity can be connected to the guiding center spin and the S here. And the S can be taken as some of the topological quantum number, and which characterizes the intrinsic matrix of the quantum Hall droplet. We just leave it to the last few slides, and you can take this value is unique for the Laughlin one-third state. And in this case, we can show you some numerical calculation about the density distribution across or near the boundary. So here, this is the density distribution for simulation. And you will see that the density distribution tends to the constant value, which close to the expectation, the one-third, that is the filling factor fixed by the one-third state. So this density distribution is uniform and is pinned down by the filling factor in the block. But we see that the density distribution near the boundary has a finite fluctuation. And here you see that the density distribution derivates from the uniform density one-third, as shown by the dashed line. Okay. And the next step, according to this density fluctuation around the boundary, we can define the dipole moment across this boundary. As I'm showing here, this dipole moment around the boundary is quantized to the one-third state, as shown by the red dashed line is the expectation value for this theory, and the blue circle is very close to this red dashed line in the theoretical prediction. So that means here the numerical calculation can also prove that the dipole moment around this one-third boundary is close to the theoretical prediction. So that means the dipole moment around the boundary for Laughlin state is non-zero. Okay, so here we show you that around the quantum Hall state, or around the boundary separating the vacuum and the quantum Hall state, there should be finite electric dipole moment. And the dipole moment, the value of this dipole moment is fixed by the Hall viscosity. And here, if you are not familiar or with the Hall viscosity, I would like to remind you that in the hydrodynamic picture, the origin of the viscosity is from the response of the quantum liquid to the geometric deformation. So here, for example, for the quantum Hall state, you can calculate the viscosity from the response of the quantum Hall liquid to the geometric deformation. And in another case, if you follow all of these calculation in the linear response theory, you will reach the conclusion that the Hall viscosity actually related to the guiding center spin, which is a topological quantum number, which is unique different topological state. And actually, so in the quantum Hall state, fractional quantum Hall state, the Hall viscosity is a topological quantum number. It has many connection with, for example, the topological shift or the guiding center spin, which describe actually the geometric property of the quantum Hall state. And this is this has been uncovered by many classical papers that the Hall viscosity is a topological quantum number similar to the barrier phase or the Chen number for different gapped topological order. Hall viscosity is also unique. It's different for different topological orders. And also in very recently, we also come up a general method to evaluate the Hall the guiding center spin and Hall viscosity for different fractional quantum Hall states. That is, we have two different methods. We use the different method to obtain this result. First, we can start from the model wave function for different fractional quantum Hall state. Under the Dan twist, we can extract the Hall viscosity and the guiding center spin analytically from the Dan twist deformation. Another case, we also perform the numerical calculations, and the numerical calculations also confirm the theoretical expectations. So in our calculation, we confirm that the Hall viscosity and guiding center spin are the topological numbers and unique to the different topological orders. Okay, so here I briefly summarize the our expectations here on the interface between Pfaffian and anti-Pfaffian topological order. So first, we expect we have some emergent edge mode around the interface. In this weak coupling limit, we see the edge mode are simply divided into two groups, but in the strong coupling limit, that is when the causal particle can tunneling through the interface, we expect all of the counterpropagating edge mode, the charge mode, is gapped out, and what's left on the interface is Majorana neutral mode. And the second effect we expect on the interface is the electric dipole moment. And we elucidate this the value of the electric dipole moment is fixed by the Hall viscosity. And the Hall viscosity is some kind of topological quantum number, which is uniquely determined by the guiding center spin. So since the guiding center spin is the quantized value, we expect that the electric dipole moment emerging around the interface between Pfaffian and anti-Pfaffian topological order is a quantized value. Okay, so this is our expectations. And next, I would like to show you some of the numerical calculation and computation to validate the above two theoretical expectations. Okay, so what we use is the following method. First, we prepare, we use such kind of, we call it as a cut and glue method. So at the first step, we can prepare one of the Pfaffian state in the matrix product state form. As shown, I use the cylinder geometry, working on the cylinder geometry, and write the Pfaffian wave function in the matrix product state form. Okay, and we, using the similar method, we can prepare another anti-Pfaffian state in the MTS form. And then at the second step, we just cut these two states into two halves. And then we glue one piece of the Pfaffian state with another piece of the state from the anti-Pfaffian state. And then we can create an interface region or domain wall between the Pfaffian and anti-Pfaffian state. And at last, we just fix the leftmost side as the Pfaffian state and fix the rightmost side as the anti-Pfaffian state, as shown in this cartoon picture. And then we left the intermediate region as the interface region, and then we use the density matrix renormalization group as a variational solver to get the energy, lowest energy configuration in the interface region. Okay, so this setup has many advantages. First advantage is that we can get the Pfaffian state and anti-Pfaffian state in this system automatically using the DMRG variation. And here we do not need any empirical knowledge or input from the other series. So we can just check our expectation unbiasedly. So the second is that the intermediate region of the state near the interface can be solved numerically, and this is based on the macroscopic Hamiltonian from the Coulomb interaction. So that is our obtained the macroscopic state is independent of the model Hamiltonian, our model wave function. That means our interface is really energetically lowest configuration in this calculation. We do not need any input from the empirical knowledge from the model wave function or model Hamiltonian on the interface. Okay, so here I would like to show you the main result from the numerical side. Here, this plot shows the density fluctuation across this interface. On the leftmost side, this is the Pfaffian state. On the rightmost side, this is the anti-Pfaffian state. And here we just using the net density, that is, we already extracted from the uniform density distribution mu here. So you see that on the leftmost side and the rightmost side, the density fluctuation tends to 0. That means it is smoothly connects to the Pfaffian state and not anti-Pfaffian state on the both sides. And around the interface, the m equals 0 marks the interface in the middle, in the middle. So this is the interface region, and we see that there is a finite density fluctuation appears here around the interface. And we see that on the left side, we find the electron-rich region as shown by the red arrow. And on the right side, we find a hole-rich region near the anti-Pfaffian side. Okay, and if we count the total net density accumulate around the interface, we will find that the total density accumulation is 0. So that means we don't have the net charge mode around the interface. So this is the charge neutral condition as we show you in the effective edge theory, that all of the charge mode has been gapped out, and the only left around the interface is charge neutral mode. So here the calculation also confirms it. So there is no net density accumulated around the interface. And the next question is that we do find these density fluctuations. And is this density fluctuations is trivial or it has some topological origin? So next, I would like to show you the dipole moment accumulation around the interface. So this is the integral procedure. On the leftmost, we integrate this dipole moment from the leftmost side to the rightmost side across the interface and gets the accumulate dipole moment across this interface. And this is the obtained accumulate dipole moment around the interface for different length scale on the for the different length scale for cylinder geometry. And you will see that the obtained result as shown by the circle is very close to the theoretical prediction, which is shown by the blue dashed line. So this blue dashed line is plotted by this theoretical expectation, as I showed you above, that the dipole moment per length is equal to the Hall viscosity over the external magnetic field. So here, Hall viscosity is defined by the difference of the Hall viscosity between the Pfaffian state and anti-Pfaffian state. And this can be also connected to the difference of the guiding center spin from two different topological orders. And here we see that in by the proper definition of the unit as the minus e over 4 pi, the charge dipole moment is close to the unit 1 in unit of the e over 4 pi. So this is also validated by our numerical computations. And so here our main conclusion is, on the numerical side, we can validate that there is a quantized dipole moment around the Pfaffian anti-Pfaffian interface. And we also elucidate that this quantization is due to the quantization of the Hall viscosity or guiding center spin for these two gaps. Okay, so at last, we would like to go back to the experiment as I showed you in the first section, and discuss how to connect our work to the experimental explanation. Okay, so let's come back to the Pfaffian anti-Pfaffian puddle state as I introduced you. So that means if we look at in real space, in some of the region we have the Pfaffian rich region, and in other region we have anti-Pfaffian rich region. And here the boundary as shown, there is a black dashed line. So this black dashed line shows you have chiral neutral mode, and the 4 arrow means we have 4 Majorana neutral mode around the interface between Pfaffian and anti-Pfaffian state. Okay, so this is predicted by this paper, and according to our work, that means we propose that around this interface, in addition to the charge neutral mode appears, we expect that we have some more detailed structure on the interface. That is, we expect some of the electric dipole moment emerging around this interface, together with this charge neutral mode. So here the blue arrow defined by the electric dipole moment, and this electric dipole moment always heading from the anti-Pfaffian state pointing to the Pfaffian state. Okay, so that means we propose this puddle. So the puddle made of the Pfaffian and anti-Pfaffian has this detailed structure, which is overlooked in the previous theoretical proposals. And according to our picture here, that means if we consider the realistic experiment condition, inevitably we have the random disorder potential in the experiment samples. And then if we put this kind of the puddle structure on the disorder potential, there should be some additional energy scale, which comes from the coupling between the disorder potential with the electric dipole moment here. So according to our theory, that we have two competing effects in this system. One is from the energy gain due to the coupling between the electric dipole moment, as I show you here as a blue arrow, to the disorder potential. And here, interestingly, we found that the energy scale E1, the energy gain, is proportional to the length scale of the interface, which we call it the L domain here. So the L is a typical length of the interface of the puddle state. Okay, because the dipole moment only appears around the interface, not in the bulk. So only appears on the interface. So this value should be linearly proportional to the typical length of the interface. Another competing effect is from the non-level mixing effect. That is, when you consider the non-level mixing effect, the party-hole symmetry is broken. So this will introduce the energy difference between the Pfaffian and anti-Pfaffian state. That means that previously we just considered the Pfaffian and anti-Pfaffian state is energetically degenerate. But in related conditions, Pfaffian and anti-Pfaffian state has a small energy gap or energy splitting. And here in the Pfaffian anti-Pfaffian puddle state, this energy cost due to the non-level mixing effect should be proportional to the area of the puddle. That means that the energy scale should proportional to the area, or the L square. L is a typical length of the puddle. So the L square is proportional to the area of the puddle. So this energy cost should be proportional to the L square, or the area of the puddle state. And if we combine these two energy scale together, we will immediately see that we can define a critical length, LC, here. That means when the size or typical length of the puddle is smaller than this critical value, we found that the energy gain due to the coupling between the electric dipole moment and the disorder will dominate the physics. That means the puddle state can be stabilized. And in the other limit, if the puddle size or the domain wall size is too large, that means in this case, the energy cost due to the Pfaffian energy and anti-Pfaffian energy cost due to the energy splitting between the Pfaffian and anti-Pfaffian state become large. And if this energy cost is too large, it is not a favor to the puddle state or Pfaffian anti-Pfaffian mixed state. It favors the uniform Pfaffian or anti-Pfaffian state in experimental condition. But this only occurs that when the typical size of the puddle state is too large. So in a word, that our consideration is that if we consider the electric dipole moment around the interface for the Pfaffian anti-Pfaffian puddle state, due to the coupling to the disorder potential, there is a condition that this puddle state can be stabilized. That is, this typical length is smaller than a critical value. And we estimate that this critical value depends on the detailed information about the number level mixing effect, but it always around the larger than 100 in unit of magnetic length. We believe this is large enough for the experimental condition. Okay, so we also performed some numerical calculation in the disorder system to show that this puddle state actually indeed occurs in the numerical calculation when you consider the disorder potential. This is a partial evidence that the puddle state between Pfaffian and anti-Pfaffian can be formed under the experimental conditions. Okay, so this is last slide. And here we study the interface between the Pfaffian and anti-Pfaffian state, and our main conclusion is there is an intrinsic electric dipole moment emerging around this interface, and we identify the driving force to form this electric dipole moment is due to the Hall viscosity difference between two topological orders. And also, based on this simple picture, this simple discovery, we propose that the Pfaffian anti-Pfaffian puddle state can be energetically favored under the experimental condition due to the coupling between the electric dipole moment to the disorder potential. So yeah, so that's all. So this is main message from our work. Yeah, and I would like to thank my my collaborators and all the input to this project. Thank you.
Okay, thank you very much. You said the 50 minutes, you're right on time.
Okay.
Great. Okay, let's have some questions from the audience. Is there any questions? Pinaki, yes. You can just unmute and ask. You don't have to raise your hand.
Okay. Hi, Vezu. Fantastic talk. Thank you very much. I have two questions. Okay. One is regarding your last point that you have these puddles being created by disorder.
Yes.
If it's energetically favorable to have these puddles, why don't they form spontaneously? For example, I mean, I'm not very familiar with this field, but it seems to me like it's similar to what you have for the Pierce transition, where every single bond is distorted. Why wouldn't you have something similar here?
You mean how to create the disorder potential? Is this your?
or why do you need a disorder potential
Oh,
if
okay.
there is an energy difference between the two scenarios?
Oh, okay. So yeah, so what we expect that, as I show you, so we expect there is a dipole moment emergent on the interface. And next we expect this dipole moment can introduce some energy scale. This energy scale can stabilize this state. This is our expectation. So here one of the mechanics we can consider or in our mind is disorder potential. This is random. Actually, this random potential creates a random electric field. This electric field could couple with this dipole moment. If so, they will introduce an energy scale. And this energy scale is energy gain for this puddle state. We argue this can stabilize this puddle state. This is argument, or you can take it as argument. And in this slide, what I show you is that we perform a numerical computation. That is, we consider this is from the exact diagonalization, we consider a sample with disorder potential. The W is disorder potential. So you see that when the disorder potential is strong enough, we indeed found this kind of the puddle-like state, electro-rich region and the hole-like rich region. So we believe this is a partial evidence to support the puddle state can be stabilized when you have the disorder potential. If you don't consider the disorder potential, you expect that this state is uniform. You don't have this puddle structure.
I see. So the disorder, the energy difference arises from having these dipole moments at the boundaries.
Yeah.
Okay.
Yeah. Actually, in this system, for this field, there is another competing effect. That is the lambda level mixing effect. Actually, this effect will introduce energy cost to form this puddle state.
Right.
Yeah. So the key question is how to overcome this effect. If you don't consider this energy gain effect, it is natural to have that. If you consider this lambda level mixing effect, the puddle state can never happen, because this, if you form this state, always cost energy. So this is why in one of the paper from the assignment in this PRB paper, they comment on this work, they comment on this theoretical consideration that such domain would not occur if we consider the lambda level mixing effect, because that is the energy cost. Even though this cost is small, you expect that this puddle state never happens. The uniform state should occur in this system. But in our consideration, if you consider there is a dipole moment around the interface, and if we can couple with the disorder potential, we argue there is some additional mechanism to stabilize this puddle state. This is
Am I right to understand basically what you're saying is that if you create a puddle in the ground state, the bulk of the puddle has a positive energy cost, but the boundary of the puddle can have negative energy cost because of disorder, right?
Yeah. And then you will consider the total energy.
So the total energy could be favorable if the boundary energy cost is negative enough due to the disorder, then you can create a puddle.
Yeah. This is our consideration. Yeah.
So it's like a volume law and the area law, right?
Yeah. So this is why I emphasize one is linear proportional to L, and the other one is proportional to L squared.
Right.
Yeah.
Now you said they have another question, or is this good?
If anyone else has a question, I will post it later.
Okay. So yeah, anyone else have a question? Maybe you can ask first, Pinaki.
I'm sure, Yangbo, you have many questions, because mine will be very specific to DMRG.
Okay. I actually have two questions. One is actually related to the experiment. I don't know if you are familiar. So if you look at the first slide, when they measure the thermal Hall conductance, the data shows the thermal Hall conductance kappa xy approaches 5/2 at a slightly higher temperature. So when they lower the temperature, actually it deviates, right?
Yeah.
So are you familiar with the mechanism? Is it because of thermalization or something like that? So
yeah, actually, first, I believe the conclusion is, I believe even for experimental group, they don't have the good reason for this. Currently, some of the people debate on this, but I believe no answer currently. The general argument from experimental group in this paper, they mentioned that at a very low temperature, they have some the edge state does not reach equilibrium.
does not reach thermal equilibrium. I see.
So that will lead to the thermal conductance will higher than the expected value. So this is general argument from experimental group. But you know, as you know from the Stephen Simon, so he argued that if you can think about this data is from the non-equilibration, okay, and then he argued that you can also expand the experimental observation from the anti-Pfaffian state.
Okay.
That means, you know, if you reach the equilibration, the thermal conductivity for the anti-Pfaffian state is 3/2, but 3/2 results from 2 minus 1/2, right? Because you have 2 1 1 3 1. Yes, so the 1/2 from the counter propagation of the edge mode. And if you consider the non-equilibration, the minus sign can be changed to the positive sign. So this will give you the correct answer for the.
So his argument is that you don't need puddle or particle Pfaffian, even for the conventional anti-Pfaffian, you can see.
So this is his argument. You just based on the anti-Pfaffian state. If you accept the edge mode does not fully reach the non-equilibration. And in his argument is one of the Mariana mode, only one mode. There are 3 modes in the edge mode for anti-Pfaffian, but only one mode does not reach equilibration. You just change the sign for 1/2, you will get 3/2. And you can think about this picture. You will consider 2 Mariana mode change the sign, and you will get even higher value for thermal conductance. But you know, so
there are a lot of debate on this, I guess.
Yeah, there are a lot of debate from the Demi Friedman, and yes, but I have to say, currently for this value, even for experimental group, we don't have the answer for this. But here we just take their conclusion, just take their message that this is close to some fractional value here as our starting point for.
Maybe a quick follow-up question is that in your puddle state formulation, do you require exactly 1/2 of the quantum Hall liquid to be Pfaffian and the other half to be anti-Pfaffian for you to see this 5/2 thermal Hall conductance?
Yeah, I think so, because but this depends on the condition. If you accept here, so theoretically we know for Pfaffian this is 7/2, and for anti-Pfaffian this is 3/2, right? And if you want to construct some 3/2, you need some equal
proportions.
Yes, average these 2 together, right?
Sorry, just 1 minute. Can you come back in 30 minutes? So does that mean that the disorder has to be nice enough for you to have an exact balance of the 2 types of quantum fluids? Or
yes. Yes, maybe. Yes. Here we just assume the disorder on average, this is the white noise like, so on average this is 0, so just to have some fluctuation. Yeah.
Okay.
This is our.
Okay, great. Yeah. So any other questions? If not, maybe Pinaki, you can ask about DMRG. I also have a question about DMRG. I'll ask later.
Okay.
Okay.
Yeah.
First of all, can you please, just the Hamiltonian, the form of the Hamiltonian you have. So this is just the edge Hamiltonian.
Oh, okay. So yes. So sorry. So this Hamiltonian is edge Hamiltonian, but this is just for explanation how to construct the Pfaffian and anti-Pfaffian state. So in all of the calculation in this paper, we just use the Coulomb interaction as our Hamiltonian. So, sorry. So I didn't write down the Hamiltonian exactly here. So we just use the Coulomb interaction as a Hamiltonian, yeah, to get all of these
Well,
calculations.
your Hamiltonian is not just the edge Hamiltonian; it's the bulk Hamiltonian.
Yeah, the Hamiltonian is the bulk Hamiltonian. Yeah.
And here you show it's a quasi 1D system, but in the last plot you show a 2D plot. Are you also expanding to full 2D?
Okay, yeah. So let me explain it in some details. Oh, okay. So this is Hamiltonian. Sorry, I write it down here. So this is a bulk Hamiltonian. What we use to calculate all of these things. So first, this is the two-dimensional system, and in our case, we just to construct this Hamiltonian, we project the system to the lambda level. So that means here the m index is different orbitals in one single lambda level. So that means we know for each lambda level we have highly degenerate lambda orbitals. And here, this dashed line marks the lambda orbitals for a given lambda level. And so the M just labels the different lambda orbitals. So that means in this case, after we project into the single lambda level, it looks like it is a one-dimensional system, or called the one-dimensional system. So each side is one orbital, lambda orbital. So this because we choose the lambda gauge in this calculation for the magnetic field. So the geometry very looks like the causal 1D system, but the interaction is very long range in this picture. Even though the interaction in real space is short range, but in this lambda orbital space, it is long range interaction. Okay, so and then what I show you here is M is also this orbital. We just scan from the very leftmost side to the rightmost side across this interface. But each orbital is a lambda orbital, not a single point in real space.
Okay.
Okay.
Okay, thanks.
Yeah. So in some sense, even for 2D lattice, you can always write it as a 1D lattice by indexing the sides, but the interaction or the hopping will be long ranged and will make the DMRG more difficult, is it?
Yeah. But in that case, I believe the computational cost is very similar to the current case. The interaction becomes non-range case.
Is the DMRG for quantum Hall easier in some sense because you have a topological gap for the entanglement entropy or something like that?
Yes, it is. I believe the gapped state is an important reason for the DMRG can apply here, because it satisfies the area where loss of entanglement is not large enough, so the DMRG can work here. Yeah. If you study the gapless system, it is very difficult to get the converged results. So the gapped state is a really good reason. And I believe the next technical point is that the projected lambda level. We projected all of the things in a single lambda level to reduce the problem to the causal 1D structure. So this will greatly reduce the computational cost. Yeah.
Actually, yeah. On this slide, I have another question. So you're studying with a Hamiltonian that is particle symmetric, but in DMRG you can actually basically your DMRG will automatically select, I guess, randomly either the Pfaffian phase or the anti-Pfaffian phase.
Yeah.
Even though these two states have the same energy, right? So what you are saying is that a linear combination of these two states will have high entropy. That's why it will not be selected by the DMRG. Is that the reason?
Yeah. So in this calculation, so you expect that on DMRG, you can automatically get the lowest energy state at the same time. You also get the minimum entangled state, and because we always optimize the entanglement at the same time with the energy. So there were some of the argument or some of the numerical tests before, but no one can prove it. But actually, the experience is that we can get the lowest energy state and lowest entangled state simultaneously. So you have the degenerate state, for example, Pfaffian and anti-Pfaffian state here. You can think about when you these two different topological states. If you mix them, you will, even though the energy it does not change, but the entanglement will enhance because you cannot continuously tune one topological gap state to another topological gap state without closing the energy gap. In this case, when you mix them together, it is expected the mixed state has higher energy, higher entanglement. So in this case, DMRG is powerful that it seems automatically selects the Pfaffian and anti-Pfaffian state in this case.
That's actually very interesting. So what you are saying is that in this two-dimensional space spanned by the Pfaffian and anti-Pfaffian, the two states with the lowest entropy entanglement is a Pfaffian and anti-Pfaffian. It's not obvious, is it? Why are these two states having the minimal entropy?
Oh, you can think about it like this. So for topological gap topological state, especially for Carroll topological order state, if you can create the excitation, for example, we know for topological excitation, you will increase the entropy because you have a topological entanglement entropy term in addition to the entropy, right? So S equals to the area law and minus gamma. Gamma is the topological entanglement entropy. That means when you increase, create, for example, create one topological excitation, you know the entropy will increase. And at the same time, if you mix the Pfaffian and anti-Pfaffian states, this is similar to you create many uncontrolled excitation based on one ground state. And this will give you the entropy increase. So maybe this is one of the argument, just one of the argument.
Okay, I'm not sure if I understand the linear combination is creating many excitations because the energy is still the same. So if you're creating excitations, then energy has to increase, right?
Okay.
I'm just trying to think of.
Okay. So let me think about it.
Vesu, did you at some point mention that you fixed the two boundaries at Pfaffian and anti-Pfaffian?
I'm sorry. At this step, we fix the boundary to optimize the interface region.
Right. In the previous study, they didn't. They just use infinite DMRG to get the matrices, I guess, right? To get the bond matrices.
Yeah. So I think both question is when I get the Pfaffian or anti-Pfaffian state.
Yeah. So in the previous step, all the DMRG procedures are particle symmetric.
Yeah.
So there's no picking of favoring of any Pfaffian or anti-Pfaffian, but miraculously, when I do DMRG and scan and minimize the energy with some truncation, the ground state is always either Pfaffian or anti-Pfaffian, randomly, I suppose, right? You don't know if you
almost randomly in our calculation, almost.
So that's suggesting in this subspace, the Pfaffian and anti-Pfaffian are quite special. It's probably interesting. I don't know why.
But why is that surprising given that it is the ground state?
But these two states have the same energy. So if you don't do any truncation, then they will you'll get the linear combination, a random linear combination of the two. Right. So because any linear combination will have the same. So the DMRG is just minimizing the energy, but at the same time, they have to do some truncation of the bond matrices. That means you are giving a disadvantage to a state that is highly entangled, because when you have a highly entangled state, truncation will introduce more error and increase the energy, right? So because you're throwing away certain eigenstates in the entanglement spectrum.
Yeah.
But why is it any different from if you say you simulate a magnetic system? Why is it any different from spontaneous symmetry breaking?
Spontaneous.
I believe for example, for quantum magnetic system, this is similar. So in quantum magnetic system, for example, when we have the time also symmetric magnetic system, for example, if you have the Carroll spin nuclei as a real ground state, if you use DMRG, you will find DMRG can automatically select the time also symmetry spontaneous breaking state as a ground state. if the ground state is corresponding case, for example.
Mhm.
So the
In
so
that
the
case
general
also,
knowledge are very similar.
yeah. So in that case also, is the DMRG suggests that the automatically selected states are the states with a minimal entanglement.
Yeah.
Right?
Yeah, you can find the symmetry spontaneously breaking state.
Right. I just wonder if there is an argument or a way of intuitively understanding why those chiral spin liquid or the Pfaffian anti-Pfaffian happens to be the two minimally entangled states in this Hilbert space. To Pinaki's question is, if you just do diagonalizations, exact diagonalizations, then you will get a random linear combination of the two states.
Yeah.
You will not get any spontaneous symmetry breaking unless you introduce in the Hamiltonian a specific small term to break it, right?
Yeah.
But DMRG is interesting because you are still starting with something that is fully symmetric, but spontaneous symmetry breaking can occur because it's an approximation, because it's not an exact diagonalization. It's giving a disfavor to a highly entangled state. It's quite interesting.
Yeah. So yeah, it is approximate method, but somehow it can give you something unexpected. So exact diagonalization is exact. In that case, it just restore all of the symmetry for exact diagonalization.
Yeah, because your truncation somehow breaks the symmetry.
Yes, truncation just like something you perturb the system, something like that. But in exact diagonalization, you don't have all of these things. You just restore all of the symmetry, all of the things that the Hamiltonian has. But in this case, truncation somehow perturb this system or something like this, and randomly will force the system drop to some minimum. Like that.
Yeah, it's just interesting. They selected the most interesting states. I would expect some linear combination, a particular linear combination which minimizes the entropy, right?
Yeah.
Turns out this happens to be the most interesting Pfaffian and anti-Pfaffian.
Yeah, I believe people, when the minimum entangled state was first proposed around the 2010, 12 and 2013, I believe some paper discussed about it, but I don't believe that is proof. Or
you can do numerics. So you just take a linear combination of Pfaffian and anti-Pfaffian, calculate the entanglement entropy as a function of 1 minus lambda Pfaffian plus lambda anti-Pfaffian. Then you plot the entropy as a function of lambda to see the minimal values occurs at lambda equals to 1 or 0. Has anyone done that?
No, I don't know any study on that.
Okay, but it's doable numerically, right?
But I don't know how to linear combine these two states in MPS. Maybe one can do that.
But just for
principle, it can do.
I'm saying exactly.
Exactly. You can just do exactly for small systems to see what happens.
Oh, you mean exact diagonalization?
Yeah, probably.
If you request that, I did that before, but not for this system, but for the quantum magnetic system for corresponding case. In that case, I did it using ED exactly. So you can create two ground state from exact diagonalization, and you can linear combine these two, and you can search in the phase space, and you will find that the minimum entropy state related to the corresponding state that breaks the time reversal symmetry.
Oh, okay.
Yes, I did that on Taurus, but in lattice system before.
I see.
Actually, this is how we calculate, for example, modular matrix using exact diagonalization method before. That is, when we calculate the ground state manifold using the ED, and then we need the additional procedure to select the minimum entropy state. We just randomly combine them and search what kind of the coefficient can give you the lowest entanglement entropy, and this will give you the state for the state for the real state or carry the topological content.
I see.
Actually, this is how we perform in ED. If we want to calculate, for example, the topological information like the modular matrix. But here in this problem, we didn't try it.
Sure. I mean, numerical you can always try. I would just wonder
Yeah.
if there is a physical understanding without doing numerics to know that the state has a
maybe-
minimal entropy entanglement.
Yeah, good question. I think about this before, but I didn't get much better understanding on that.
Okay.
Yeah.
Okay. Thanks. Yeah. Okay. Yeah. We are, I guess, a bit open. Any other question? Maybe any other questions? If not, let's thank Zhu Wei for the very interesting talk.
Yeah. Thank you. Thank you. Yeah. Hopefully, I can visit you sometime on site.
Yeah. Yeah. Maybe the second half of the year. Let's hope.
Okay. Yeah.
Yeah.
All right. Thank you.
Okay. Thank you. Yeah.
By the way, Ezu, if I may just say something completely different.